Okay, so the recording has started. We can I'm sharing my screen. So wait, sorry, my laptop just get disconnected. Let me okay, thing has started. Sharing my screen. Okay, I hope you can see my screen, right? Mm, me maximize this. Okay, so this is week 6, 1st March. So in week 5, if you missed, we broadly discussed how neural networks work, and we discussed the forward pass algorithm, the backward pass algorithm, or the backpropagation algorithm, and we kind of did a training, validation, testing, not validation, we did only training and testing on a MNIST dataset. Okay, so MNIST is a handwritten digit dataset. So I have the slides here, I guess. Yeah. So this type of dataset was there. Okay, and they built a very shallow model just like this. So three hidden layers, two hidden layers, one output layer, in total 3 layers, and we kind of get around how much accuracy? Let me check. Yeah, we get around 98% testing accuracy on 30% test set, right? So this week we first uh, start with train train validation testing. Okay, so why this train validation testing is done instead of only train test? Okay, test and then we'll follow up with the other this week's material like these and tree regression trees and all, right? And we'll try to do a hands-on examples of them. So let's start. And then, by the way, the week 5 and week 6 assignments, we will discuss it next week. Okay, after week 6 deadline is over. Okay, and I have uploaded week 5 question here. If you want to take a glance at previous runs week 5 question, you can see it in the drive folder. Okay. Okay. So I hope we are recording. Yeah, everything is okay. Now, so what is the problem with the general train test method? See, let me just and why what do I mean by train validation testing? And there is another method we will discuss as the last if time permit, that is cross validation. Okay, which is actually which is actually week 7's content. But okay, it will be better if we discuss it here because the hands-on examples we can then modify it based on the cross validation logic as well, right? So let me start with why train test split is not a good idea. Okay, and when it is a good idea and when it is not. Let me just connect my graphics. Okay, so just add another page. drop, right? Fine. Now, okay. So, so what we did earlier was train test split, right? Train and then another set test, another set was test. So we have the entire data. Okay, we split it into two halves, and because the training needs more data, right? These algorithms, whatever algorithm you took, let's say machine learning algorithms need less data. However, like so, if you give more data, it will likely be improving. Okay, so most of the time the training data is greater than training data is greater than test data most of the times. Okay, and a general rule of thumb is around 70%. So it doesn't look like 20%. So 75%, 70% is around here, right? So 70% will be our training data and 30% will be our testing data. So it was good if we just go with this approach, right? So what is the problem of not using this approach all the time? See, so so what is the general machine learning loop we work in? So there is a computer, right? So there is, or let's say there is this algorithm A, right? We give him or we give that algorithm data, right? And then it trains and it gives us what? It gives us metrics, right? Metrics for evaluating metrics for evaluating the model, right? Or the algorithm. So here we came into picture, right? The supervisor, or let's say not the supervisor, we can say this is like a human in loop thing, right? So there is always a human in the loop. What he does, he observes the metrics or like see what the model is performing on test data. Let's say test data, right? Test data, and then based on that change the model parameters. So based on that, human what it does, it modify the model or modify the architecture. Let me zoom in a bit to it. I zoom in here. If you yeah. So what we do, we modify, right? So here this human in the loop, this component actually uh, kind of adjust the model based on the testing performance you are getting. So there is a leakage of information. So the human in the loop, this component observe the testing metrics, right? Even if the model doesn't see the testing data, but the component which is, let's say, modifying the model can have access to the testing metrics, right? So based on that, we can, let's say, if I have less testing accuracy, I can just increase another layer, right? And that can give me, let's say, another 2% testing accuracy boost. But it is not like that modification is not good for the entire distribution of the data. It can be good for the specific test set we have, right? So in this case, there is a information leakage. Okay. Now to encounter this, what we do, what is the more appropriate approach? Let's say this is my data, right? I can split it into three groups, three sets, and the general distribution is this 60% for training data, 20% for testing, sorry, 20% for validation, and 20% for testing. Okay, so and if the data is very big, right? So there is no sense of putting this much data to, let's say, for 40% data into validation and test. If the data is, let's say, in the order of 100 millions or 10 millions, this order, then we can also have if kind of distribution of training, testing, and validation, like 70 and then 15, 15. Okay, that is also the valid split if my data is more. So this valid, so the idea is this validation and test set should have enough samples to represent the actual data. Okay, so if my entire data set has a lot of samples, then only putting 15% of the samples in, let's say, training set and 15% in test set is enough for representing the true data distribution. Okay, but if my data is less, then it is something like this. So what 60% would go for training, 20% would go for testing, and 20% would go for validation. Okay, so this is training set TR. Let's say this is validation set and this is testing set TE. Okay, so this is why training, like train test validation, is a good alternative of train test split. Why? Because train test split, because of the human in the loop nature of training these algorithms, right? It can have a information leakage issue with the test set. Okay, so what we do for training, validation, testing, what is the change in this case in the training loop? So instead of seeing the test matrix, we see validation matrix now. Okay, so the validation set is used for the human in that loop to kind of perfect its model architecture. Okay, so he can only see the validation matrix, validation performance of the model, and then based on that tune his model architecture or whatever algorithm he is using. And he can only use the test set once. And so what he does actually, or what the human does in that loop, is he modifies the model until he get the maximum validation accuracy. Okay, and because the validation and the test set are sampled from the same distribution, we assume that the validation set is it's kind of similar to the test set. Okay, but these samples are different, so they are coming from the same distribution. That is the, like, the idea, right? So if I have maximum validation accuracy, let's say, then I should also have maximum testing accuracy, right? So that is the logic. So we will use the validation set multiple times to tune our model or tune whatever architecture you are training, and then only use test set for once. Okay. Okay. So this is why train test validation is used in real world settings. So because we cannot use the test set for tuning the model. Okay. And how you can use it? So there is, so for coding, you can use this logic. So you can use the train test split for once for train and test validate, like train test validation together, and then again split test validation to validation and test. Okay, or the train, let's see, valid test. No, there is, I guess, no uh, inbuilt function for this, because we can use the train test split function itself for 3 splits. Okay, now let's see. So this is train validation test. Now let's just see how decision trees work. Okay, and then we can just use, or we can just do an example of a decision tree and use the train validation test method instead of train test. Okay, so decision trees. So decision trees are like this. So let's say um, I have, there is a root node. Okay, so there is a, so these are like, uh, let's say you have a data set. Okay, so A is the parameter, B is a parameter, and then you have a label L. Okay, Now these can be real values, these can be categorical values also. This can be, let's say, belongs to real, and this can be belongs to a category of variables. Okay, category of values. Okay. Now labels can be, let's say, 0, 0, 1, 1. Okay. Let's say, let's just do an AND gate first. 0, 0, 0, 1, 1, 0, 1, 1. Right. So AND gate means 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, and 1, 1, 1. Right. This is the kind of truth table for an AND gate. So let's say this is my data set. Okay. And I want to construct a tree over this. So what I can do, I can take A first, right? And how I will take A, or let's say any other thing is based on the value. Based on which value, if I split the data, I will have less chaotic nature in the labels. So if I just split with 0, right? So this is my split. See, in my labels, this is completely 0, and this has some chaotic nature in it. So it can be 0 or 1 both, right? Now let's split with A first. So if I split with A, my root parameter would be A, right? And let's say my check would be, let's just remove this. A is equal to 1. Okay. Or let's say A greater than 0. A greater than 0. Okay, this is my check. Now this can be a root node. Now A greater than 0, for 0, for 1, right? And let's divide the data set for both the cases now. Uh, for 0, so the data set would look like AV label 0, 0, 0, 1, 0, 0, right? You can see that my labels are already 0, 0. So there is no split required further. Okay. So there is no confusion among the labels. So my label becomes 0. So here is a leaf node. This is a leaf node. Okay. Leaf node 0. Now, let's say now here, right here, what is the data set, remaining data set? A, B label, you have 1, 1, 0, 1, 0, 1, right? So see here, if I split over 1, 1 cannot be splitted, right? It's only 1. So we have to split with B. Now if I split with B, it can be directly separable, right? Thus this half has only 0, and this half has only 1, right? So the decision parameter would be B greater than 0. Now B greater than 0, what are the possible values for this? For 0, this is for 1. If I go with 0, it is the leaf node can be 0. And if I go with 1, the leaf node will be 1. Leaf node would be 1. So this is a decision tree for the AND, like AND gate. Okay. So if you just pass any value, right? Let's say if I pass 1, 0, for example. So 1, then 0. I reach the leaf node 0. So my output will be, my prediction will be 0. So this is how a, you can say okay. This is how a decision tree is constructed. Now what happens, let's say, if I cannot split it further, for example, if one scenario occurs when I have only one variable A, and it can have, let's say, only 0 values, right? And my label would be uh, 0, 1, 0, 0, 1, something like this, right? In such cases, if I cannot split, I will take the majority. So here it is 2 1s and 3 zeros, so I will take 0 as the output. So what it does, so even if I don't predict correctly for some instances. I can predict correctly for most of them. So for instances where we cannot split further and there are mixed answers, right? Mixed labels, we have to take the majority. Majority. Writing is so majority. Anyway, so this is how these trees are constructed. So there is this algorithm called I forgot the name of the algorithm. Okay, I'll let you know in the chat WhatsApp group. So this algorithm has a name. Okay, I guess um, TD3 or something. Okay, I have to see. Let you know around. And regression trees, what we do instead of majority, we take mean. Okay, until we split the data, we can get, let's say, less chaotic data, like sub data sets. We can split it, and later on, if we cannot split it, we just take mean instead of majority for regression. Okay, the construction looks similar here. Yeah. Okay, so get the idea of how the trees are constructed, right? Now let's see for a data set, weathers, right? For example, a weather data set is there. We can see how the tree is entirely constructed based on that data. We can print the trees, by the way. Okay, let me open up the activate um, email, and then we have okay. So we have this weather.csv data set, okay, like which is a toy data set for printing out these entries. Yeah, this is just copy it. Text file. Okay. So what the data set is representing is based on some weather parameters. Let's say outlook, whether it is overcast, rainy or sunny, whether the temperature is hot or cool, or the humidity is high or low, whether it is windy or not. Based on this, whether I will go and play outside or not. That's the entire data set. Okay. So we can just now let me zoom it in. Okay. Okay. So read CSV, weathers.csv. So this is head. I can just print the entire data because it's not that much big. It's only 13 rows, right? Or 14 rows actually. So now let's try to build a decent tree from this. Okay. So from sklearn dot tree import decent tree classifier, because it's a classification model, right? So because my play is a categorical variable, yes or no. Now, one thing we have to do before we can pass it, I guess we can pass it. Let me see first. This entry classifier. And what are the, so let's not test it for now. Let's just see what is the entire tree that is getting built on this data. Okay. So X should be data frame dot drop columns play. I can only drop the play column. Play P should be capital small, and that is my X, right? And Y is equal to df dot. I can just do play dot headers. Okay, now what do they look like? I'm not intentionally encoding them into zeros and ones. Okay, let's see whether the model can itself encode it and take these categories into account, or we have to manually encode it. We have to see. Okay, let's just send this data as it is for now. X, sorry, tree. Let's say dt recent tree. Now, what are the parameters here? Okay, so Gini means information gain. Okay, so that chaotic thing I was telling, if my so in difference between the entropies is called Gini index. Okay, so what is entropy? Entropy is basically H log, like P of X log of P of X, right? Minus P of X log of P of X. So if my data set has only one class, it has the lowest amount of entropy. Okay, and if my data set has, let's say, equal split of two classes for 0 50%, 1 50%, then it has highest entropy. Okay, and Gini means the difference between, so before split and after split, what is the difference between the label set in terms of entropy? Okay, base split means you will do the base split of whichever split has the maximum Gini index, we will split at that value. Okay, so just like I like from the visual like visual explanation, we split it at where we split it at 0 first for A, and then we split it at what 0 at B, right? So by visually seeing, we can observe that okay, my data set gets less chaotic if I do this type of split. Similarly, the model does the same. So best means choose the best split. Max depth means you can also see max depth. What it does, you can also specify how many depths you want to traverse, how many depths you want to build the model. If you let the model build for a very long depth, right, it would overfit the data. Okay, so what sometime is done is, let's say, keep the maximum depth to 10. After it reaches the 10, it takes majority, or for if it is a regression, it takes a mean of the label. Okay, so yeah, so max depth is kind of limiting the maximum depth of the tree. So for now, let's not touch it. And minimum sample to split is also 2. Minimum sample for leaf is 1. That means if you don't set them at lowest, it can split only a data set with only 2 rows, and one leaf can only have, let's say, one data point, right? So single data points can be allowed. Okay, so if you just make them let's say 10, right, so it will create a leaf whenever it reaches to a data set which has length of 10. Okay, so these things are sometimes used for regularizing the model so it doesn't overfit the data. Okay, these are take a max features, random state. So see, these models have a random state. Okay, so if you don't set the random state, it can happen that for two consecutive runs you can have different models. Okay, different structure of the tree getting created. Okay, so what can be a good example? For example, let's say uh, two features, if I split them at some value, it can have the same or equivalent Gini index. Okay, so in that case, for one random state, it can choose to have feature 1 as the split point for first node, and for the second run, it can choose the second feature, whichever has the same or exact same Gini index. Okay, so yeah, so better to set a random state for these type of models. If you don't So there, if there are assignment question which doesn't mention random state, be aware you can, for multiple runs, you can have multiple different type of trees getting created. Okay. So yeah, so if you don't see random state mentioned where you have to create a decision tree, ask the TAs once. Okay. Class weight CLP, that's fine. So let's put random state to be 42. Okay. Okay. DT dot fit. Now see, we have not done any encoding on the data, right? We have not, let's say, make overcast 0, rainy 1, sunny 2, like this. We didn't do that. So we can just pass X and Y. Let's see what happens. It gets an value error. Fine. So what it could not convert string to float. So it needs floating point data to be operational, right? So by two ways, I can make this data workable in two ways. One is by just encoding overcast as 1, rainy as 2, and let's say sunny as 0 by this, or we can have this one hot encoding. So what do I mean by one hot encoding? Yeah. So if a feature, let's say F1 has three options, let's say A, B, and C, right? So whenever my data is A, I can represent it like 1, 0, 0. It's like a binary representation of the thing, okay? C means 0, 0, 1. And let's say B means 0, 1, 0, something like this. So you can also represent it like this, or you can just encode A to be 0, C to be 1, and B to be 2, right? So there are two type of representations. So for now, let's stick to this one so that we can like interpret the tree properly at least. So what we can use for this, can use a label encoder from sklearn dot preprocessing import label encoder. Now what it takes, LE label encoder equal to label encoder. It doesn't take any parameter. Label encoder dot fit transform. Fit transform means it kind of gets these dictionaries created within the label encoder object. Okay. And it tracks those encodings. For example, if it assigns overcast to be 0, it tracks that data in a dictionary. We'll see what it tracks. X. Now if I X would be in 1D array, got a 14 cross 4 instead. Now I have to pass it column by column, I guess. Let me see. If I pass DF directly, it doesn't work, right? But if I pass play, it works. So that means I have to run 1, 2, 3, 4, 5 label encoders for all the columns. So what we can do, um, we can have a label encoder list, right? Now for every column in df.columns, what I do, I create a label encoder for column, append that label encoder, or let's say create a dictionary for this, right? Label encoder dot, or let's say whatever column I have, right?
Excuse me,
Column.
sir.
Yeah. Okay.
Sir, I actually was able to hear you just now because due to your network issues. Can you just give a small recap of what you are doing till now?
Okay. So we are currently, see, the model doesn't take string values as input. Okay. So we are kind of encoding the string values to zeros and ones and twos. That's it. Okay.
Yes, sir.
Okay. Okay. So So column, so LE column equal to we can add that label encoder because we want to track it, right? To see what is the encoding it used. Let's print that in print. I will print the encoding later on. Now TF.
So what does encoding basically mean?
We'll see. We'll see. Column equal to, sorry. Uh, sorry. Column dot fit transform column. Now just let's copy the DF one so that we don't lose DF. DF copy or DF encoded. Encoded is equal to DF dot copy. Okay, so one thing you should know that these objects have are aliases. Okay, so if you just name them, it doesn't work like normal variables. You will create an alias. So you should always do this dot copy if you want to create a separate copy of the data frame. So this mistake is like very common in exams. Okay, so DF encoded, I will apply everything on DF encoded. Yeah. Now if I run this, DF encoded look like this. See? Whereas my DF, actual DF look like this. Now you know what encoding is, right? Because the models cannot take strings as input. So we have to manually make them to numeric values. Okay. Now I also have all the label encoder stored here, right? So what I can do, let's say Outlook, right? Outlook, and I can see the mapping dot see get params. If I just, okay. Yeah, see, this is the mapping. So overcast is 0, rainy is 1, and sunny is 2. It's just confirm. Yeah, overcast is
Huh?
1, overcast is 0, rainy is 1, and sunny is 2. Yeah. Similarly for other two, let's say play, right? Play. What is the encoding? No is 0, yes is 1. Okay. We can also, let's say if I want to predict, right? It will predict in zeros and ones. Now we can use the same, let's undo delete. We can use this same uh, inverse transform. Okay, we can also do inverse transform. Inverse transform of, let's say, Outlook. Sorry, rainy. You have to give a list. It is the y coordinates. Oh, sorry, it has no, right? No. My contains previously unsealed values, no, right? It should not be a. Oh, sorry, guys. The network got disconnected. Okay, it's back now. I guess you can see my screen. Now I can also do inverse transform on a list, right? And it will give me what y contains. What's this? Okay. So it should be we should be passing an NP array. Okay, so play doesn't take no. Anyway, let's see. We'll see it later. So anyway, play and yeah, these are the encodings. Let's go with the modeling now. So instead of DF, we should use DF encoded. Okay. Now ds entry will fit the data. Now we have the ds entry, right? Now dt dot predict. If I just let's say predict on X, right? We'll see the training accuracy of the like training accuracy. If I just predict on X and what is Y, you can see it matches every entry, right? So the prediction at the Y is exactly same. Fine. Uh, Now let's print the tree. So we have to use a package, I guess. Uh, Plot tree.
Sir, prediction can be 100%.
So we are predicting on the training set, right? We are predicting on the training set. So we haven't split the data. We just use the entire data for training. So it overfits the training set. So now it predicts all the points correctly for the training set only. We don't have enough data for testing this, right? So you'll see for a big data set, because this data set only have 13 or 14 entries, right? It's not a good idea to like do training testing on this. We should go with a larger data set later on. But this is to just print how the tree is created. So you can use this from sklearn tree plot tree and how it give you output like this. Fine. Our model name is DT. Yeah, so this is my model. If I just do plt.show, so x3 means the third value. Okay, so we have, yeah, outlook is the x0, temperature is x1, humidity is x2, x3, and this is level. So up to x3 we have splits. And see one thing, um, we can split with the same variable again, right? So uh, so these are kind of before the leaf nodes. Okay, so it has two leaf nodes. Okay, sample one, value 0 and 1, sample 1. Uh, it has 4 samples. Okay, let's see how the tree is getting printed. Understanding the structure of the tree. To proportion equal to true, because it clutters the map. Okay. Okay, now it is clear. So earlier what happened, these leaf nodes are so congested, it looks like it was um, kind of going over this node, right? Now these are leaf nodes. Okay. And see what is the kind of percentage that we are having. Here it is 7% of the data, 7%, 7%, 7%. Here it is 21%. And here you can see it is 26.8%. And where it splits as x0 less than equal to 0.5, right? Now less than equal to 0.5 means what? 0, right? So it can only have a valid value of 0. 1 and 2 is in this path. So x0 0. Let's see x0 0 whether all the values are 0 or not, or 1. Actually 1, it should be 1, right? It doesn't say the actual sample. Okay, the value equal to 0 and 1, fine. Okay, so let's see for x0 equal to 0, what is the label? So x0 is equal to 0, x0 is equal to 0, all the values straight here, right? Everything is 1, right? So for this percentage of data, how much percentage is it? Everything is 1. Out of 14, we have 1, 2, 3, 4 values. So 14, so how much percentage? 4 divided by 14, it is 28.5% data. If I have x0 to be 0, then everything should be predicted as 1, right? And see, exactly same thing happened here. If x0 is equal to 0, then 28.6%, it's rounded it up, right? It's 28.57. Everything gets put to this node, this leaf node, which has around 28.6% data, and everything has to be predicted as 1 based on the data. Now, if it is not like this, right? If it is grade 2, 1 or 2, then it checks for the second x2. That means x0, x1, x2, x0, x1, humidity. And what it checks, same. If it is 0, now see here you can see the entire tree structure. If it is 0, it will go this way. If it is 1, it will go this way. Right? So let's see, if it is 0, it goes this way. Fine. So what was the combination? Uh, x0 can be 1 or 2, right? Then x2 has to be 0. We'll go to see the let's say x2, this leaf node. Let's see what it means. So now here it means x0. X0 means same outlook is less than equal to 1.5. So 1 is also considered here. 0 and 1 is considered here. Only 2 is considered here, right? x0 is equal to 2. So x0 can be only 2. Now this give me a leaf node. And what is the statistics? We'll see what the exact value is. It gives me 21.4% of the data. 21.4% of the data. And everything is some value. So it's not written here. We'll see. Okay. So from the data. Now I can actually uh, run a query on the data set and get the percentage of this data. Okay. So what I can do, we have encoded, right? So to get this percentage of the data, what I can do, I can just do like this. Dot ilog. Ilog can give you access to the columns. So 0 means 0. If I pass a array 1, 0 and 1, right? It gives me 2 columns. So for 0, this is 0, and it can be, it is equal to, see what is the like Boolean expression I'm writing. It can be is equal to so I can just pass without the bracket. Yeah, it can be is equal to 0, or it can be is equal to 0, 1 or 2, right? So to write that expression, I have to copy this, do an binary AND operation, and do 2. So this is my first expression. For the 0th column, it should be 1 or 2. It gives me a kind of uh, false data, right? Now, so why it is false? Or sorry, not or, not and, or. These are our or operations. It cannot be both 1 and 2 together, right? Yeah. So What happened? Oh, we have to do. Okay, so OR is this operation for Boolean OR. Okay, that OR was logical OR. This is Boolean OR. Now the second x2 is equal to 0. That means another or no, sorry. Then we are traversing through the uh, next branch, right? So it should be an and same. I just copy this. GF encoded second column should be 0, right? And sorry, and the third is the zeroth should be 2 again. Zeroth should be 2. So this is my entire path for the tree, and this is my set of data. Is it okay? Now let's filter that part of data. Okay, so you have, it's not a leaf node, but where we have gone less than this. X2 should be 0, 0, 1, and X0 should be 2. Here it is 1 and 2, fine. And then here you came as X2 is equal to 0. Then X0 is equal to 2. X is equal to 2. Is it not equal to 2? Is equal to 2. Less than is equal to 1.5. Now X, no, okay, so this part I guess it's not a leaf node. Okay, so we let's go to this leaf node. Okay, so X0 is equal to 0 and 1, and then we go to X3 is equal to 0. X3 is equal to 0. Guess we are doing something wrong. Oh. This OR operation will be like this. So DF encoded 1 or 2. 2 is equal to 0. Then 0 is equal to. So we are doing something wrong. We are not providing all the necessary uh, branches. So let's see. 0. We have 1 and 2 for this branch. Okay, 0, 1 and 2. Then here we have 2, 0. 1 and 2, 2, 0. Here we have 0, 2. It should be a so 0. Oh, now it is correct. See, here this was the mistake. So we had to cover this this OR operation because it was one node, right? We have to cover this OR operation within a bracket, otherwise it will mess up the entire computation. Okay, so it is how many values? Three values, right? So 3 divided by 14. How much percent? 21.4%. So how much data we have here? 21.4%. So let's also go there, this path also, just so that we are confirmed. So after this, x instead of going here, we will go here. So the last, this should be changed. This should be 0 and 1. So we have to cover it with another and pasted. Now this should be 0 and 1. Now where we have traversed here instead of here. Okay, now less than 0. So for 0 it is 7%. x3 0, x3 0, and x3 0. Again we have, oh sorry, here it will be or, yeah, only one value, right? And it is yes. So this was 21%, and this one is 1. So 1 divided by 14, how much is it? It is 7.1%. So you see this data is 7.1%. Right? Now you see the entire dysentery, how it is constructed, right? Same as we have discussed for the OR gate. Because it was for a small amount of data, it is easier to understand. But for a large amount of data also, it does the same thing. Okay. So it tries to go column by column, check all the possible splits, right? And see uh, whether my Gini index is increasing or decreasing. So how you can compute Gini index? If you have, let's say, an array 0, 0, 0, 1, right? And after split, you have an array of 0, 0, another split is 0, 1, right? So what you can do, you can compute the entropy of this array and do a minus. So you are improving, right? So your entropy should reduce, minus entropy of 0, 0 plus entropy, sorry, ENT would be entropy of 0, 1. Yeah, so this is the computation of Gini index. Gini of split. Let's say the split is at so what is the split here? The split is at some other parameter, not on this parameter. This is the label, some parameter p on some value v. If I split, my label set splits like this. Okay, so one catch is there. Let's say if there is so here the split is kind of 50-50, right? So you do 0.5 times this and 0.5 times this to just weight the entropies with respect to the length of the label set. But there can be scenarios where my label set splits like this. Okay, so in that case I have to multiply it with the equivalent factor. So here the weight factor will be 3 by 4, and here my weight factor would be 1 by 4. So this is how a split is computed for a particular parameter, for a particular value. If my split, so they track all the Gini indexes for all possible splits. Okay, and take best. So if you can just go to the descent tree parameters, here you can see we are computing based on Gini index, and the split we are taking as the best. So we'll compute all possible splits and then take only the split that has the best Gini index again. Okay. So this is the kind of how descent trees are constructed. Now let's practice something. And regression trees are same, only instead of majority you took. So for Gini index you took MSE, mean square error, and for what your instead of majority you took mean. That's the total, like the entire difference between regression trees and descent trees. Wait. Okay. So now let's see an example of descent trees. Okay. And we will use the train validation test set test logic instead of normal train test. Okay. So what is a example data set for descent tree? There is this uh, so it has to be multiple. Okay, weather. So there is this full weather data set also. Okay, which has I guess 20 years of weather data. So you can use that data set. Yeah, weather history. This one, right? Download. It's a 16 MB textual data. 16 MB is lot, so it has around 20 years of this weather data from I guess somewhere in California. Okay, let's just save it for now. Okay, read CSV weather CSV, and this data set we can use it for both classification and regression, because the target you can see if I just print out the data set. Yeah, right. So this is date time. So date time is important if you are doing a time series analysis. Okay, and how it is different, you see it is computed hourly. So it's an hourly data set. Okay, per hour you have a data point. So let's say we want to classify whether a particular day will be rainy or not. So we have to make the data set, and these are pre-processing steps. So so we have to make the data set compressed for a day level data. Okay, and uh, okay, summary, daily summary is here. That's fine. Mm. So let's say I want to classify this summary. This is my label column based on the like these all the data points, right? Or let's say not summary. Let's say I want to have this precipitation type to be my label. Let's see what the data labels look like. Humidity, visibility, loud, pressure. So these are meteorological data. We have to use it um, for the features. Okay, we can either use uh, this perception type or this summary to be the label. Let's see what these columns contain. Unique. So these are the unique values for the summary column. Now for the other column, only rain, snow, and none, right? So with it will be either raining or snowing. That's it. So let's only predict rain or snow. Let's not go into all these things. Okay. So DF columns, what are important because we want to, and what is our objective? Do a uh, day level rain or snow prediction, right? Now, what are the important features we have? Let's take the entire features set for now. So columns, this to bracket it. Okay. Now date format, we'll see. Summary, I don't need this one, right? This one is my level. Temperature, apparent temperature, humidity, wind speed, this degrees, visibility, and how my data look like. Let me just take a look of the data, whether it is all numerical or something. Okay, it's everything is numerical. Only the perception type is running. Preset type, something like this. Okay, temperature, cloud cover, daily summary I don't need. And then the last column, that is my level. So these are my column, right? I have to sum first. If I just take only those columns, what is the key error? Play. They should not be here. I have to read it. Oh, sorry, columns. Now you see, I have this date column by which I can take an average of the data, right? So what I have to do, create another. So this is my DF cleaned. It's not cleaned anyway. Just name it cleaned for now. We have to get this date information out, right? So I am facing a lot of network issue today. I don't know why. My campus Wi-Fi is getting disconnected multiple times. Anyway, DF cleaned. What I have to do, I have to get the date out of this column, right? So how I said I should do that. Formatted date dot apply. We can just apply a lambda function that splits the data. Let's say this is the date, right? So there should be a space after the date and then the time starts. So I can just do e dot split at space and take the 0th column, right? It gives me all the date. Now I have to make this another column, date, right? Sorry, DF cleaned. Now I have this extra date column, right? Now what I can do, I can group by. So I can get the groups first, and then we'll see dot group by the date column. So this give me groups, okay? Groups, and what the groups look like? Groups dot, let's say, groups, and these are the groups of indices. So for example, for this date, I have all these indices. Next date starts here, right? So how you can get a particular group? Let's say get group, and then you pass and now you have that slice of data which have 2026-001 date. Sorry, 0101 date. And all the dates are same, right? So the entire group is here. Now we have to find a way to process this data and have only one value from it. See, we can only take, so for the label column, we can take majority. For the other columns, other numerical columns, we can take an average, mean, for example, right? So this is, let's say, DFGR. We have to process DFGR dot, what are the feature columns? This is not required. Temperature is needed. And this is the label column, right? Label column. Now for the all the feature columns, we can just take mean. These are my means of the of the features, right? And then for the label column, I can just take uh, what is majority. Majority is mode, right? Mode cannot be computed directly here, is it? Yeah, mode can be computed directly. So what is the maximum repeating value for the label? We can just do data is equal to and cast it to a dictionary, right? And data label also have this value. Now my data look like this. So I can process all the groups and add them to a list, and that list can be casted to a data frame of only having. And also let's keep the data date, right? Let's also keep the date column for now, and this is the group name, this one, right? My data looks like this now. So how I can run this logic to all the groups? See this, process data for gr in group dot groups. So you get the how you can get the dates dot keys, right? That's a entire dictionary. And if I just print the groups, in the groups, you see these are the dates I'm getting, right? So I can just copy paste the entire logic within this and just replace the let's say date, right? Replace the date here and date here. Now data has a particular process data for a particular date. I can just append it to the process data append. Yeah. df processed is equal to pd dot data frame process data. So now my data looks like this. See, it's date wise, the temperature average, everything, the features averages and the label, right? Now let's see what is the value counts, right? Value count. So it is the percentage of the data. It's all rain. Okay, so if I just take mode of the data, so it's like most of the time it is raining. Okay, so majority would not work. So if I do majority, it will make all the labels to be rain. Or we are doing something wrong. DF. Oh, okay. Wait. It should be DFGR. Okay, DFGR equal to group data, mean, label mode, Okay, now it is fine. The index 0 is out of bounds for x is equal to 0. Why? Why? Okay, we have. Okay, wait. We just run the entire thing again. So for some groups, oh, it is none. So there are three values, right? Nan, rain, and this. So we can, what we can do, we can just do a drop now here. Drop now. So that when we are reading, we remove all the nan values. Okay. Now this is our percentage. So there are 3,600 times it was raining, and 398 times it was snowing, which is okay. Now we can model, right? So what we can do, we can now train, test, split, or train, validation, split our data. So from, let's do x and y first. X is equal to a processed feature, and y is equal to dA processed label, right? It's clearer. Okay, label, I have named it as label for the next time. Okay, label. So y is this, x is this. Okay, now what we have to do, we have to split it into train, validation, and test set, and we can use the train test split from sklearn dot model selection, import train test split, and we have to do train test split twice. Okay, so x train, x test, y train, or not actually y train, x test not x uh, uh, remaining, y train, y remaining, rem, okay, is equal to train test split x and y, and so do you know what this stratify means? This size to 0.3, or let's say test size of the remaining side, I want 0.3%, and these are other parameters. We should random state, let's keep it 42, shuffle true. Stratify means the ratio of the labels, the different labels in training set should be same in the other set. Okay, so if there are 10 training instances and 5 snowing instances, it should be similarly proportional in the remaining set as well. Okay, so it will be, let's say, 6 rain instances and 3 snow instances. So the ratio becomes 0.5 in both cases. So this, if you don't pass stratify, then it randomly splits. So there is no guarantee of this same percentage of the labels. So it's better to keep it true for now. So what is the problem? Singleton array true cannot be considered valid collection. A valid collection where singleton array true. Oh, stratify, you have to give the y level. Okay, y. Okay, not true. So let's see what is X train. X train is this. Okay. Uh, Y train. Fine. Um, so one thing we should do, we should actually, um, because there is only two instances, we can just apply a dictionary here. Apply, let's say map a dictionary, rain to be 1 and snow to be 0. So we just hard coded the labels, okay, to be 1 and 0. Others are already numerical, so no problem there. Now it's 0 and 1. Okay. Now from the remaining set, we can just do the same thing. Instead of x, we pass x remain, and y, we pass y remain. And here it is validation test, validation test. And stratify, if I want to stratify, I will just pass y rem. Okay. Okay. Now we have three sets: train, validation, and test. Now modeling. We are not scaling or anything. That is not currently our focus. We are not scaling the data, and particularly because we are working with descent they don't care whether you scale the data or not. So scaling is important only for methods that use gradient descent, okay, or that use gradient based approaches. Because in case if you are not scaling the parameters, then my metafold which I am traversing by the gradients becomes stretched. Okay, so because the descent tree models don't use gradient based methods, so if you even if you don't scale the data, it will be no impact, like it will have no impact on the performance. Okay. Okay, so recently from sklearn dot tree, and just try to remember this path, recently classifier. Now let's set some parameters. Okay, let's set that my maximum depth and my leaf sample, I have to change it. Okay, my maximum depth, let's say I allow the model to build a depth up to 10. Okay, so if it reaches depth up to 10, it will take majority. That's it for the leaf node. Now minimum sample split, let's say for splitting a data, it has to have at least 10 samples, otherwise just get a majority. Okay, and minimum samples for a leaf node, let's say we can have at least 5 samples for a leaf node. If one sample means it's overfitting, we should not have good testing accuracy in that case. Okay, now dt dot fit. So there is this cool concept of feature importance also. We'll discuss, right? Extrain, extrain, and then we test it on I red train, predict, extrain, and let's just copy week 5's the score, right? Classification score and everything. Don't have to rewrite it. Yeah, so we have all the metrics to compare our model, and let's say metric train is equal to compute classification model y train and y bred train. So y bred train. Oh, it need the y also. Yes, y train. Okay. So what is my accuracy of training? So my precision is 0.9. So let's just print it. be better to see. Oh no, for every key comma value in a trend, print key colon print. So this is just a fancy way of printing my dictionary. Okay, value. Sorry, dot items. Yeah. So see, my precision is 0.9, which is fine. Recall is 0.9, that is 0.99, that is also fine. Accuracy is also good. And that is what is expected, right? It's on the training set. It's almost 100% accuracy. It only misses two times for the snow. And for the rain, for the snow, it misses 14 times. For the rain, it misses only two times. Okay, remember 0 is snow and 1 is rain, right? So let's see what is the accuracy for test set, and what, by the way, what is the decent tree look like? Decent tree proportion equal to true. Sorry, plt dot show. Yeah, so this is the entire decent tree, and you can actually save this tree in a high resolution format. Okay, so plt dot show, instead of plt dot show, you can do plt dot save fig, and then let's say pass tree dot png, and also pass dpi is equal to 300, let's say. Okay, now if I go here and say see tree.png, it's a very high resolution image, right? I can just zoom in and see. I can also export it in, let's say, 1000 dpi, but still it's a now I can see the values at least where the uh, let's say the decent node has been split on which entry of the column and on all these things, right? So yeah, so this is the entire tree, and you can see we can only go up to level 10. After that, it just squashes the data and take majority. I don't think it has gone to table 10. 1, 2, 3, 4, 5, 6. It has only grown up to level 6. Okay, so this is my tree. Let's also see what is the validation, and we'll try to tune our model based on our validation accuracy, not the testing accuracy. Okay, so instead of, no, we'll not fit the model, we'll try to predict on the validation. Valid. Have to just, okay, so it is in the validation also, it is around 99 point something percent, right? And let's see whether we can improve it. So it is 99.4. We'll see whether by changing some parameter would improve my model or not. Let's say my maximum depth can be go up to 20. Okay. Has it changed? No, 99% 0.4. Even if the, let's say the model has been changed, right? But my validation accuracy doesn't change. Let's say let's not set these values. Let's not set any value, let's say. Okay, now my validation accuracy becomes 1. Okay, and my model is something like this. It's a very big model now. My training accuracy is also 1. Let's see what is my testing accuracy. Now let's say I'm happy with the model. My validation and training both becomes 1. Okay, now let's see what is my testing accuracy. Oh, sorry. This should be valid. Okay, so it is 98.4. Okay, let's go back to the previous one and see what was earlier. So it was 98.4. If I go with 10 depth, it is only 98. So it was better if I don't pass any parameter. So basically, I'm not restricting the tree. It can grow as big as it can as it want. Okay. Yeah. So it's the huge tree. My validations are 99.4 F1 score. It's a good F1 score. Let's also check what is the metric for testing. Test. Okay, it is 99.4. So we are happy. Okay. So it's 99.4, and after this, I will not change my model. So usually what happened after I see the testing accuracy, I just go and read like let's say modify the model architecture again, right? Modify the model architecture, change some parameters, and then see whether my testing accuracy improve or not. Here what I did, I see the validation accuracy to tune my model. So up to validation accuracy, there is a data leak. Okay, so even if the model doesn't see the validation data, it is kind of getting that information through me, right? But for the testing set, after I see the testing accuracy, I will not touch the model again. Okay, so this is the can see train validation test like training process. Okay, here I stop stop training the model. I'll just export the model, use it for let's say prediction in a production environment. After this, the model is not changed. Okay. Okay. So so now let's go for a regression task. Okay. So regression task could be exactly same instead of these categorical labels like this category, instead of categorical labels you will have the metric would change. Instead of Gini, what is it? From scalar, I guess mean MSE, tree, import, decentralized regressor. Decentralized regressor. Yeah, my criteria is squared error. So MSE, right? I will take best, everything is same. Instead of Gini index, you have squared error. So what would be changed for computing the split? Where is that equation? Here, right? So here, this one, we cannot do like this, right? Uh, let me check. I have implemented this descent earlier. This regressor. Uh, mm, it's hard to find it now. Let me see. Descent regressor loss equation. Is it regressor? Okay. So impurity minus right impurity, left impurity. So here impurity means to see earlier entropy was there, right? It doesn't need any kind of label for it, right? So here impurity means MAC of the uh, like I guess it's from the mean minus the entire data. Okay, that's the impurity. How much it is varying from the mean impurity. If I just do a search, growth tree based node is defined relative reduction in impurity. If none, then unmuted. Okay. So it is computed, typically calculated using MSE, which represents the average square distance between predicted values and actual values at each node. Okay, so you take the majority, okay, or mean for here it is mean, and what is the like MSE from the mean. So imagine a node with the average value 5, compute the MSE from the mean. That is the impurity. Got it? So what would our equation would change like this? Instead of entropy, this is the measure MSC phi and value p. We are splitting parameter p at a value p. My label set is this, or any real value. It may not be categorical values because it's a regression task, right? So what will be my mean of this? And you take the MSE between the mean and the value. MSE. This is one initial impurity, and then for the left side you do the same. Let's say, and you weight the values based on the number of data points, right? So here it will be similar. Just copy paste this part, and let's say the split is like this. Similarly, plus, and here let's say only have one value, right? One. So this part mean would be the impurity would be 0, and here the impurity will be also 0. So you have maximum gain. This is the gain. Okay, and based on this gain, whichever gain, or let's say this is also known as this loss part, this one, right? Whichever value at whichever parameter has this gain as maximum, you split at that point. Okay, you can actually code these logics. It's very easy. So let's say I have 5 parameter. Let's say p1, p2, p3, p5, right? p4, p5, and they have value v1, v2, v3, v4, all of them. So the loop would look like this: p int uh, p1, p2, p3, p4, and p5. All these are parameters for all of their values. V1 for v in Q1, V2, V3, let's say only 3 possible values are possible. You compute the gain for all of them, and after the loop, you get the maximum, right? You will so instead of representing them as values, we can also do data left, data right, data, and this is also data. This is data left. So this is general representation that you will see everywhere in the blogs or anything. Data right, add value v, and then you, after this loop, you get maximum gain for whichever parameter. Let's say you get maximum gain for P3, V2, right? Then you split the data at this point. So my descent parameter, my node would look like this, P3 less than equal to V2. Okay, now if you are below this value, you have a data left, and above this value, you have a data right. This is how the tree node will be constructed. Again, this will be a recursive computation for the right part, left part. Again, recursive until you reach a terminal point where there is, let's say, only one sample, or you have intentionally set these parameters here, right? Minimum sample should be 5 or minimum split should be 10. If you intentionally set those parameters, it will stop at that stopping point. Let's say minimum sample split is 10. So whenever my data samples becomes left or right becomes only 10 values or 10 rows, then it will stop there and take mean. Okay, so yeah, mean. And for descent tree classifier, it will be, instead of mean, it will be uh, mode, right? Most repeating value mode. And this gain equation would change, obviously. Instead of this MSE mean computation, it will be Gini index, which I have explained earlier, right? Okay, I guess this part is clear, right? There is no doubt in descent regressor or classifier. Guys, if you have any doubts, clarify it now. Okay, so I take it as a there is no doubt. Now let's so now this part is pretty clear. So how you can handle missing values? So so if you have, let's say, NaN values, right? So how we have handled for the previous data week 6 example, how we have handled missing values here, drop now. So we have dropped all the missing values, right? And this is it is particularly not a good approach. Why? Because you lose the data. Okay, so how much data is NaN? Let's see. Uh, if I just So if the label is missing, then we cannot do, right? Then we cannot populate labels based on some statistic. But if the features are for this data set, the labels are missing actually. DF columns, and this is the label column. Value counts, right? Okay, so it is no. Oh, okay. Why DF? So where we have na values. Okay, let's see where the NaN values are. Maybe it is not in the label. Then oh, DF dot is na. So it gives me a true false uh, thing. Okay, now if I just pass df, we'll see this is the missing data. So there are a lot of rows which only have NaN values. Okay, so here we cannot do anything because the entire data is NaN, right? There is no data in it. So, but in case of a, let's say, where partial data is missing, right? So in that case, there can be multiple ways to deal with missing data. So, and that has to be something based on domain knowledge. For example, if I know that a particular wait. If I know that a particular phenomenon uh, has a property of normal distribution, right? For example, if you so if you see, um, if you just ask people to, let's say, uh, pick a number from 0 to 10, okay? So a good prediction would be most of them would predict at 5. Okay, so if you ask participants to pick a number from 0 to 10, you will get a normal distribution like this. If you just do this count plot, you will get kind of a this type of a normal distribution. Okay, so from the physical phenomena, I can surely say that temperature change over an year would be a normal distribution. Okay, if it is in a tropical area, it will be mostly like high temperature. The mean would be at high temperature. If it is, let's say, in a let's say close to let's say Antarctica, right? So it will be the mean temperature would be lower. But anyway, it will be, because it's a physical phenomenon, a physical reading that you are getting from the environment. It should follow the normal distribution in some mu and some sigma, with some mu and some sigma, but that is not known to us, right? But so what is mu? Mu is the which data has the maximum probability of repeating, right? Maximum probability of repeating. So if I am let's say filling temperature data, let's say T1, T2, T3, I have this type of T100 data points, and then I have a missing point, right? Then I have a missing point, and then I have T11 sorry 102. 101 is missing, right? Again, I have continued data till T1000. So because I know that this temperature parameter follows normal distribution, right? So I can just take mu and replace that value for the missing data. Okay, another approach this one is the one approach. Why it is useful? Because okay, I know the distribution is normal. Mu has the maximum probability of repeating, so I'll fill that value. Now someone can argue that okay, no, T100 and T102, they are adjacent, so there should be a value T100 plus T102 divided by 2. There should be a linear interpolation between T100 and T102, right? This is also a valid choice. Okay, so when, let's say, I don't have any domain knowledge, so let's say I don't know whether the distribution is um, normal or skewed or t distribution, anything, I don't have any parameterized for, let's say, assumption or any domain knowledge on that parameter, right? In that case, I can go with the linear interpolation given my time difference. So sampling this temperature and this temperature doesn't have too much time difference in it. Otherwise, it's a better idea to replace it with mean. Okay, so let's say this is from month 1 and this is from month 2. Then replacing T101 with mean is a better idea. But if it is from day 1 and day 2, then doing a linear interpolation would make more sense. Okay, so there are a lot of these are called imputing. Okay, the machine learning term for handling missing data is imputing. So there are a lot of this type of imputing objects in Python. We can just go over them later on. Whenever, let's say, we have a data set that has a lot of missing values, and we know that the columns we have has some kind of pre-known or let's say well-defined properties, like it should be a normal distribution or it should be a skewed distribution, like this. Okay. Okay. So I guess we can take some questions now. If you have any doubt till now, you can clarify now. Okay. Otherwise, we will just move to. So cross validation, I can just tell you the idea for now. Maybe later on we can do an example on this. So any doubt till now?
Excuse me, sir.
Yeah, go ahead.
Just want to have some query regarding assignment 6 questions. Entropy.
No, assignment 6 I cannot discuss it right now, right? Because it is still due. So if I just discuss assignment 6, so it will make it like unfair advantage to this session, right?
Okay, but entropy
So
and how to find entropy from with the help of example is not discussed in any of the
okay,
video.
so entropy, so that I can tell.
Information gain and entropy. How to
That I can tell. So entropy,
Yes.
you can just search entropy equation. It's
Hmm.
very easy. Minus P of x log of P of x. Okay. So entropy probability entropy equation probability. So this is the equation. Okay. Summation of P of x log of P of x. So how you can compute it? Let me show you one like for a kind of example.
That is regarding yes or no kind of thing. You have
Yeah.
to separate the probability of one class and zero class. Is it like
So let's just say I have three classes. Okay.
okay.
0, 1, and 2.
Hmm.
And let's say 0 instances are 5, 5 0 classes. These are counts, number of zeros, okay? Number of ones are, let's say, 6, and number of twos are, let's say, 2. Okay, now how I can compute entropy? So I have to get the probabilities of these things. So P of 0 is 5 divided by 11 plus 13, right? 13. Then P of 1 is 6 divided by 13, and P of 2 is 2 divided by 13, right? Then just plug that into that equation, that so that my entropy E of the data, this is my entire data, right, would be minus 5 by 13 log of E base. Okay, so it can be log 10 base also, just the base is changed, so it will be factor of 1 over log E base 10, right? So we can just go with log E base. Okay, so log E base 5 by 13, then minus 6 by 13 log of 6 by 13 E base, and then again minus 2 by 13 log of E 2 by 13. That's how you compute entropy.
Sometimes it is used log to the base 2.
So log to the base 2, you can, so see, the difference is what? The scale would be changed. So the relative computation is same. So log 2 base you can always also use. So
log to the
yeah,
base 2 can also be used.
yeah, log 2 base, log E base, log 10 base, everything you can use. Only the thing that would be changed is the scale, right? If you just see
How
log
can we decide which base is
10
to be
base A, log 10 base A means I guess log E base A by log E base 10, right?
used?
So you just multiply it with a constant factor, you just the scale is changed from two different bases. So I guess if you are if you are going with log 2, go with log 2 everywhere. If you are going with log 10 everywhere, then your
Okay.
final result will be same. And if you are confused on which scale the data is, or let's say the option is given, right? In that case, just compute 10 base, E base, and 2 base, three of them, and just check once. It will be constant, like it will be consistent for all the assignments. Okay. So if the, let's say if the TS has fixed log 2 base, right, then they will fix log 2 base for entropy in all the assignments. So just
It is
see
not
once.
mentioned anywhere which base is to be used.
Yeah. So
Not in the assignment or not in the lectures.
here you see here
Yeah,
for
it is
binary.
given the log to the
Yeah.
base too. So,
For
in
binary
Google or
cases,
in
it is
ChatGPT.
log 2 base this
Hmm.
one. And see for general case, right, it is not given. For this, see
Okay.
this equation, it is not given. So not given log means it is log 10 base.
Log
Right?
10.
Yeah, and if it is ln, then log e base. So it is interchangeable. Just see whether one instance matches and then just stick with it.
Okay. We'll calculate for all the three bases, and if the answer matches for any of the MC.
Exactly.
Okay.
I guess mostly it will be log 2 base.
Log 2
If
base.
yeah, and in the lectures also see what professor has gone with,
Okay.
right? In that equation they have he should mention log 2 base, e base or 10 base.
Okay. Okay. Sir.
Okay.
Thank you, sir.
Okay. So I guess today we'll stop here. Okay. We'll cover this cross validation, and in the next day, let's say next day, we'll cover cross validation and an example of cross validation. So what I can do, we have 5 more minutes. So just let's pictorially give you a kind of overview of what cross validation is. Okay. So it's another method of testing when you have less amount of data. So see, the difference is pretty clear. If you have, you can do training, testing, split. You can do training, validation, and then testing set, right? There is another method. So it has a direct gain that my model is now unbiased, right? Model um, is model uh, wait 1 minute. Okay. It okay. So what is the gain of this validation set? My model doesn't see the test set, right? Model doesn't see the test set, so it's now more generalized and doesn't have any information leakage. But when let's say I have less data, right? So splitting, trading, testing, and validation is not an option. So let's say I have only uh, 500 data points, right? So in that case, if I just do training, testing, and validation, there is a high probability that the validation and test set would be different from the training set. Okay, and doesn't represent the training set in validation, or validation doesn't represent the test set. And it can only happen you have less data points. So for 500 data points, I can, let's say, train on 400 data points, test on 50, and validate on 50. But this 50 data points might not represent the actual data. Okay. So it is better to not waste these 50 points for validation set. Instead, what we can do, let's say this is my entire data. I can split. So there is this n fold, right? This parameter is there for cross validation. We'll see. Let's say I've split my data into 5 folds. Okay. So 5 folds, 1, 5 equal folds, 3, 4, 5. Okay. So this is 1, this is 2, this is 3, this is 4, this is 5. So 5 folds. Now there can be how many combinations of this? 1, 2, 3, 4, 5. This is the test set, okay? And training set is the remaining. So for 1, it will be 2, 3, 4, 5. For 2, it will be 1, 3, 4, 5. For 3, it will be 1, 2, 4, 5. And for these things you get, right? So if I am testing on this data, if I'm testing on this data, I'm training on the remaining data points. And it actually like loops through all possible combinations. So 5 splits means there will be 5 training sessions, and after all the training sessions, you will get a testing accuracy. So they all, let's say, testing 1, testing 2, testing 3, testing 4, and then testing 5, right? So the entire testing accuracy you will get is actually the mean of this. Mean of this, and the variance you will also get, that how much variance you can see if I am, let's say, deploying it in a real-time environment, or let's say in a real world, right? So that standard deviation also you will get that, okay, my so earlier, because there was only one test set, there are only one testing accuracy, right? Testing F1 score or anything. Here you can have mean and standard deviation of the same matrices. So F1 score, there will be a mean of F1 score. There will be standard deviation F1 score. That means, so maximum times we will see F1 score of this, and there is a variance that you can observe based on the data split, or data based on which part of the data set you are sampling from. Right, so this is a more generalized way of evaluating a model. Okay, that kind of use the entire data set for training and testing. Okay, so there can be, like, based on, let's say, random seeds and everything, these splits can give you biased results. Okay, so for example, somehow my testing set has more, let's say my testing has set has 99% of dog images, right? And my model predicts dog images correctly, so my model accuracy becomes 99%. But here for cross validation, it is not the case. For cross validation, because it choose every part of the data point as a testing and the remaining as train, it doesn't get biased observations like this. Okay, so we'll see how to implement this in scikit-learn in maybe in the next class. Next class we'll also discuss week 5 and week 6 assignment questions. Okay, and I have uploaded week 5 assignment questions in the drive. You can go and check it out, because week 5 deadline is over, right? So after week 6, I will upload week 6 questions also and discuss them in the next class.
Sir, week 5 assignment solution, sir.
It is in the drive I have shared, right?
Sir,
You are in the what?
previously I
Yeah,
unable to find the solution of previous week, sir.
yeah, this one, this folder, this drive link you have, right? It's intro to ML NPTEL drive link. I have shared it.
Yes, sir.
Yeah, in most of the, like, resources in WhatsApp, right? So you just go there. There will be week 5 assignment questions for the
Of the
previous run. So this run, week 5 already you have, right? So it was
Could you
from
please share
previous
the
run.
drive link once again?
Yeah, so you are in the WhatsApp group, right? I will share this week's resources. I will
Yeah,
include
thank
this
you.
drive.
Joined late, that's why.
Okay, 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 okay. Thank you, guys. Let me stop recording.